Hello, I will talk about MoFuzz, a fuzzer suite for testing model-driven software engineering tools. I am Hoang Nguyen from Humboldt-Universität in Berlin, and this is joint work with Nebras Nassar from Philipps-Universität Marburg, as well as Timo, Kehrer, and Lars Grunske, also from Humboldt-Universität. So, model-driven software engineering tools, that is, tools that process models, can exhibit unexpected program behavior, just like any other software. For example, here we have a class cast exception in the Eclipse UML validator utility. In order to improve the reliability and maturity of MDSE tools, these possible errors must be identified as fast as possible. However, as we all know, manual testing is very tedious, and thus an automatic approach is more preferable. One of the most popular techniques to automatically find bugs or crashes is fuzzing, where the main idea is to repeatedly execute the program under test with automatically generated inputs. Fuzzing has been successfully applied to general purpose software that process basic inputs such as integers or strings, up to simply structured file formats, for example, HTML, PNG files. The problem, however, is when we try to apply existing fuzzing approaches to MDSE software, their effectiveness is limited due to the difficulty to provide structured as well as well-typed input models that conform to the consistency constraints, not only imposed by the input metamodel, but also by the underlying modeling framework. To illustrate this problem, in the case of the Eclipse modeling framework, tools that process input models typically have an input processing pipeline as illustrated on this slide. So first, there's a parsing stage which checks whether the input model is actually syntactically valid. That is, in our case, whether it conforms to basic EMF constraints and whether it is properly typed with respect to the input metamodel. Optionally, a syntactically valid model must also pass an additional validation stage, which checks further semantic consistency constraints. And only after all these stages have been passed, the input model is actually passed to the core functionality of the MDSE tool. As a result, when fuzzing MDSE tools based on EMF, there are two challenges that need to be addressed. First, in order to actually test the core functionality of MDSE tools, the fuzzer must be able to provide inputs that are well-formed enough to pass the initial input processing stages. On the other hand, the generated input models must also be interesting and diverse enough to test many various features of the modeling tool under test. So we approach this problem by drawing from advances in two independent research fields. On the one side, we have advances from mutation or generation-based fuzzing, which provides us inspiration to effectively guide the input generation process, to effectively guide the system under test by leveraging not only structure awareness, but also coverage feedback. On the other side, we can draw from automated model generation techniques, which allow us to instantiate metamodels with varying consistency guarantees and efficiency levels, including methods that are solver-based, grammar-based, mutation-based, or learning-based. While this instantiation of the fuzzing problem to the modeling tools is fairly trivial, the problem is it is unclear how to effectively combine these techniques. So the main question we are trying to answer with our work was to find out how to effectively combine automated model generation with fuzzing. So our overall approach looks like this. So in this work, we are focusing on the Eclipse modeling framework, which has emerged as the de facto standard in the context of open source MDSE environments and toolchains. So as input, we require an metamodel of EMF, which basically specifies the language of valid input instance models. Of course, as our second input, we require the MDSE tool under test. As our fuzzing backend, we rely on JQF, which performs coverage-guided fuzz testing in Java. JQF performs a continuous fuzzing loop where test inputs are sampled from handwritten input generators. One of the fuzzing strategies that is implemented in JQF is ZEST, which is an algorithm that is able to automatically guide input generators by leveraging coverage as well as validity feedback. We adapt this input generation strategy by providing 3 custom input generation methods. Our first technique is a graph grammar-based one called MoFuzz EMF Model Gen, which attempts to efficiently cover the input domain as fast as possible. Our second and third approaches are coverage-guided and mutation-based, which thus aim to incrementally evolve inputs using coverage feedback. We implement this using 2 different sets of mutation operators, one based on the generic EMF edit API called MoFuzz CGF EMF edit, and a set of mutation operators based on consistency preserving edit operations called MoFuzz CGF CPEL. So our first approach, the graph grammar-based technique, is based on the EMF Model Generator tool, which has been recently introduced by Nebras Nassar. The tool is able to efficiently generate large and properly typed EMF models with valid multiplicities. The tool works by first deriving model transformation systems from the Metamodel in Henshin, and afterwards, these model transformation systems are used in 2 phases to instantiate metamodels. In the first phase, the model increase phase, using graph transformations, we add model objects to the model without violating upper bounds. In the second phase, the model completion phase, the partially invalid model is then completed to a valid EMF model by interacting with EMF repair. So I will illustrate this 2-phase approach on this state machine metamodel. So a state machine consists of regions, which in turn consists of states and transitions. Each transition requires at least one source and a target state, and the region has exactly one initial state. The state itself can contain further subregions and can also be a final state. So what happens in the model increase phase is that we add model elements, that is objects or references to the model through graph transformations until a predefined criterion is met. For instance, if we have reached a target model size. In the second phase, we add the missing references and objects so that the model is completed to a valid EMF model. So in this example, we had to add a reference to a target state, as well as a reference to an initial state, which were initially missing in the partial model from the first phase. So compared to solver-based methods, the graph grammar-based approach provides a good trade-off between efficiency and consistency by employing a 2-phase generate and repair approach. Furthermore, since the model increase phase uses atomic model transformation rules to add objects and references, the input space of valid instance models can be explored in a broad manner. Complementary to this approach, our mutation-based techniques aim to guide the input generation process towards interesting program regions instead of performing a broad exploration, which I will describe now in more detail. So in the field of mutation-based fuzzing, one of the most widely used techniques is to employ a coverage-guided evolutionary algorithm to produce new test inputs. First, we start with a set of seed inputs or generate them through seed generation and feed them into an input queue, where at each fuzzing iteration, we select one input and perform a range of mutations on it in order to obtain a set of mutants. Each of these mutants is then executed on the system under test, and it is checked whether the new mutants execute any new program branches. In the case that the mutants do not increase coverage, they will be simply discarded. If they happen to increase coverage, they will be added to the queue, And this fuzzing loop will continue until a predefined timeout has been reached or it is manually stopped. So in our approach, we adapt this generic fuzzing loop by providing methods for seed generation as well as mutations adapted to inputs that are based on models. So as I said before, we implement mutations based on two different sets of mutations for models. And our first set is our generic mutations based on the EMF edit API, where we use as seed generation method a simple tree grammar based seed generation method. On the other hand, the other set, or rule-based mutations, are based on consistency preserving edit operations, meaning that when they are applied on a consistent model, they will preserve the consistency. These mutations are implemented as rule-based model transformations using Henshin, and they are also used for seed generation. So the mutation operators generally implement mutations that add objects or references to the model, as well as delete objects or references, or change attribute values or reference targets. So there are also some other mutations which are described in the paper, but in this talk I will describe some, I will highlight some differences between the generic and consistency preserving mutations. So in the case of adding an object to the model, when we use a generic mutation, the mutation will add one or more objects to the containment tree of the model. And it will also prioritize uncovered metaclasses to focus on high metaclass coverage. However, it leaves the attributes uninitialized. On the other hand, if we perform a consistency preserving mutation that adds objects to the model, it will only add an object to the containment tree if no upper bounds will be violated. Furthermore, the mutation will also create mandatory children as well as cross-references to mandatory neighbors, as well as initialize all attributes in order to preserve the consistency of the model. So if we look at this example, adding an object using our mutations will yield an inconsistent model using our generic mutations, but using our consistency preserving mutations, it will yield another consistent model, because on the right side, our transitions has references to its source and target state, whereas they are missing on the left side. When performing deletions on a model, our generic mutation operator can delete any object in the containment tree, and it will also remove transitively contained objects as well as all cross-references. As a result, the mutation can result in the deletion of larger subtrees. On the other hand, using consistency preserving mutations, since they're implemented as inverse routes to adding objects, they can only be applied if deletion does not leave behind any dangling edges, which is also known as the dangling condition. Therefore, deletion using consistency preserving mutations can only be applied on the leaves of the containment tree. If we illustrate this on our previous model, instance model, you can see that using generic mutations, it is possible to delete all objects in the model, even if they reside in an inconsistent model, whereas using consistency preserving mutations, we are only able to delete the transition object as well as its references to the transition, to the states. When we change attributes or reference targets in models using mutations, using generic mutations, we are able to change the values as well as to unset the actual value, meaning that it will be set to the default value and no longer considered as set by the model. On the other hand, if we use consistency preserving mutations, we are only able to change the values but not unset them, since they are modeled as mandatory neighbors. So as a summary, there's a trade-off between efficiency and consistency guarantees. On the one hand, using generic mutations is very efficient, but as I've illustrated before, there are lower consistency guarantees. Using the consistency preserving edit operations as mutations yields higher consistency guarantees, but since we have to perform these checks, they are less efficient. So we have evaluated our approaches and we attempted to answer 2 research questions. The first question is whether MoFuzz can improve code coverage compared to the baseline. And the second research question is whether MoFuzz can improve the fault finding capabilities compared to the baseline. As evaluation subjects, we use a wide range of modeling tools ranging from code generators, model validators, model transformations, as well as model comparison and model merging utilities. All these subjects take as input instances of the UML metamodel, which is a well-known and fairly complex metamodel. Our setup looks as follows. We set a maximum target model size of 500 model elements, and as baseline, we use the EMF random instantiator, which is a containment-free based random instance generation approach. And we enhance this generator by using the ZEST algorithm to guide it towards higher coverage and validity through feedback. As a runtime, we set it to 1 hour, and to account for randomness, we perform 30 trials and assess statistical significance through the Mann-Whitney U-test. So in our first set of experiments, we have compared the coverage between the different approaches. And for efficiency reasons, JQF does not report traditional branch coverage, but instead maps exercised code branches to a fixed size coverage map and reports the ratio of non-zero entries as the map coverage. Map coverage is approximately proportional to branch coverage, and for the sake of this comparison, it's more important to compare the relative differences between the approaches rather than the absolute values. So as you can see in this table, for almost all benchmark subjects, except for UML to Java, 1 or more techniques of MoFuzz was able to significantly outperform the baseline techniques in coverage. If we have a look at these plots, which plot average coverage over time, we can also see that our graph grammar-based technique has the highest and fastest coverage. What we can also see is that the pure random approach performs worst with respect to coverage, as well as boosting it using the ZEST technique can significantly improve the performance, but it still falls short to our custom domain-specific mutations as well as the graph grammar-based technique. Our second research question concerned about whether MoFuzz is more effective in exposing crashes. So we have encountered a total of 12 crashes in our experiments. And when comparing the performance of the baseline with MoFuzz, we have found that MoFuzz either triggered the crashes at least as reliable as the baseline or even more reliably, or MoFuzz was able to find a crash significantly faster than the baseline, or MoFuzz found a crash which has not even found by the baseline techniques. So comparing the overall approaches, we find that MoFuzz finds 12 crashes compared to the baseline with only 8 crashes. But we also find that the individual techniques find a crash which has not been found by any other technique of MoFuzz, meaning that our individual techniques complement each other. To conclude, I've presented MoFuzz, a fuzzer suite tailored towards fuzzing MDSE tools. MoFuzz is implemented in 3 approaches: a graph grammar-based technique, 2 variants of coverage-guided mutation-based fuzzing, where there's one technique aims for broad exploration, where the other techniques aim for incremental evolution of the inputs. In our experiments, we found that MoFuzz significantly outperforms the baseline, not only with respect to coverage, but also with respect to the crash finding capabilities. We've released our tool on GitHub, and as future work, we are mainly concerned with integrating our approaches more tightly, but also further increasing their strengths by integrating solver-based techniques. So that's it for my talk, and thank you for your attention.
Thank you very much, Hoang. So I think we are ready to take one question. So I don't see written question, but you can open your mic or write something in the conversation screen. So for the moment, I don't see questions. So I have several questions. Maybe I can ask one of these. I was wondering if you, if there is a clear relation between diversity of generated models and coverage, because when you generate diverse model, we can think they cover more or less well, but you can have some cases where you have many similar generated models for one branch, for example, of the model. I don't know if my question is clear, but yes, you understand. Yes.
Yeah. So when we're talking about diversity, we're talking about different meta classes that are instantiated in the model. So for example, if we consider the UML validator benchmark, where each meta class is validated individually, it is of course more beneficial if we have diverse models which contain at least one instance of each meta class defined in the meta model. Since if there's no instance of it, it cannot be, or the respective code location in the validator tool cannot be exercised at all. So there's, I think there's definitely a benefit in having diverse models.
Yes, okay. Okay, so I don't know if there is one question or okay. So maybe we have to switch to the next talk. But I would like to make a last comment to your work, because I find it very interesting because it embraces several existing works, and this is very hard to make what you did. So because it's not easy to use the work of several people, several tools, and building something new and relevant and efficient on top of that.